Okay, good morning. It's already slightly easier to get a seat in here. That's good. So today we're going to continue talking about a few things that I didn't get to last week, and then we're going to start to talk mostly about almost one of the root causes of environmental degradation, which is population dynamics and population growth. And then we'll move on to some more sciencey stuff next week. All right. So I'm already annoyed with returned emails. So these are the 5 people in this class who do not have correct email addresses associated with their Rosie account. So every time I send out an email to the entire class, these 5 emails bounce back to me. And I know for sure that the second one is totally an invalid mailbox because no undergrad students still have UToronto accounts. Anyways, please fix this. Good. All right. So, tutorials start next week. All right. But regardless of them starting next week, I want to take a quick minute and just try and link in what we're doing and how some of the tutorial and assignment materials kind of emphasize what we're doing. So in your first assignment, it will require you to effectively learn to search for peer-reviewed scientific information, to summarize important points out of scientific journal articles that you find, and to cite properly. All of these things are very important. I listen to CBC radio all the time, big documentary radio thing on plagiarism in university on my drive-in this morning. All right, so this is one way to think about or to learn essentially how to cite ideas from others properly and then therefore avoid some of the pitfalls of plagiarism, which we'll talk a little bit as time goes on. Your final product will be an annotated bibliography, and there'll be some slightly more abundant instructions available on Blackboard. I can't remember if I posted it already or not. I think I did. If not, it'll be posted shortly, as will lecture kind of slides that the TAs will go over during your tutorials next week. But how does this link with the lecture material? Why do I make you learn how to use the library? Well, 2 things. One is you will have to use library materials and find journal articles and think about scientific information for the rest of your lives, and certainly for the rest of your university careers quite often. But there's not a whole lot of opportunity to learn how to use some of the resources effectively. University of Toronto has the #1 library system in the continent. Okay, we're better than Harvard, we're better than Princeton, we're better than Yale, any Ivy League school in the States, MIT, kick their butt from a library system, okay? So, take advantage of it a little bit. We have access to practically everything, and we have access to everything from the leisure of your couch if you have wireless internet at your house, for example. All right, even if you are not on campus, you can get access to all University of Toronto library resources as long as you have your UTOR ID that you normally carry to get into your email address and stuff like that. So how does it link, though, otherwise, other than having a good skill to learn? Well, one of the biggest thing it links with is carrying out the scientific method, which we talked about quite a lot last week. And how this links in with the scientific method is coming up with the questions in the first place. So when you think about science has I'm not trying to be degrading right now, but science has very little to do with what you don't know, but has everything to do with what everybody in the world does not know. Okay? And so part of your university education, for example, is to bring you up to a certain par with what people know by the time you're done university, with what people know in a certain field. And you can really talk quite fluently about what goes on in a certain discipline of science, social science, humanities, whatever you happen to be in. But at this point where you are now, and how do you learn to get to that point? Essentially, the #1 way to learn to get to that point is read like crazy. And read like crazy in something that you're interested in. And where is the repository of all of the scientific information that we actually know about? It is not on, run-of-the-mill websites and Wikipedia. Wikipedia is wrong all the time. Wikipedia is written oftentimes by people who are massively biased. There's an anti-Wikipedia site you can go on and find out who writes the stuff on Wikipedia. You can see that Walmart's, written by everybody from Walmart. All right, not an extremely unbiased view, for example. And there's, things I know lots about. You go on there, it's totally wrong. So sometimes that's not very, or not, oftentimes it's not very reliable. The most reliable spot are scientific journal articles. And scientific journal articles go through what we call a peer review system, and then they get published if they're lucky. Probably 25 to 30% of the scientific articles that get submitted for publication actually get published. Who peer reviews such things? And what is peer review? Peer review is other experts in a certain field that will read some scientific study, see if it's any good, and then give somebody at a journal advice on whether or not they should publish it. Who does this? 90+% of the people who do it are professors like me. So I do them all the time. I do 3 or 4 of them a month, probably. Journal articles. And then I publish journal articles myself, and they go through the exact same process. I can get studies done with some of my students, for example, submit them. They might get published a year later. These things are quite slow. They're speeding up with the internet and things that you can do on there, but they're still relatively slow and very rigorous process. So it's extremely rigorous. There's probably 3 or 4 professors or people who, government researchers who are very talented researchers who will read articles for free. So I do all of this for free. Essentially, it's just part of my job in a way. But I mostly do it at night in my free time because I like it so much. And so you do this stuff, you submit it, and somebody will collect a bunch of reviews. And if everyone says that it's total junk and that they didn't have a control and they had too many variables and they weren't figuring out how to do something properly, their correlations all sucked, etc., it won't get published. And you'll never see it as a piece of information that will increase your knowledge. And if you never see it, then fine, because it was no good in the first place. But the stuff that does get published is the stuff that builds up our knowledge. And the stuff that builds up our knowledge also starts to fill in the gaps for things that we don't know. And so therefore asks the questions about things that we actually need answers for. But regardless of getting answers, there's always new questions. And oftentimes when you do science, especially really groundbreaking things, you end up not necessarily answering nearly as many questions as you generate. And so you end up generating more and more questions. So the reason that this links in with what we're doing is that there is a scientific method to figure out how to carry out the scientific method and specifically how to come up with the questions and then therefore formulate the hypotheses you need. You need to rely on very good information. All right, so that's kind of the end little bit from last week that I wanted to talk about. All right, what is environmental science? We didn't really get there last week. What is environmental science? Environmental science is this, if you ask 10 different environmental scientists what environmental science was, you're likely to get at least 9 or 10 different answers. The ongoing broad answer is that environmental science is a very interdisciplinary science, meaning that it doesn't necessarily have its own foundations in anything. There's not a lot of overarching environmental science theories within environmental science as an individual discipline. But what environmental science does take is from multiple disciplines at the same time, and then thinks about questions and does science that answers questions that cross disciplinary boundaries. And so, for example, I do a lot of stuff in water. So, one of the disciplines I look at is hydrology. But I also do a lot of stuff in geochemistry and biogeochemistry. And so I have this other stuff that I look at, how pollutants are in the environment, where they are, what reactions kind of go on. I do a little bit of toxicology. How do animals get affected by some of these things? So some biology, for example. And I don't do as much social stuff, but I end up getting into it sometimes. You know, there's some political things or legislative issues that come along that you pull from as well, which actually gives a little bit of oomph to what you're doing and makes people actually interested and a little bit more worthwhile. And so as an environmental scientist, for example, I pull all of these things together from these different disciplines, which makes environmental science a bit of a science for people who are a little bit more jack of all trades. However, most environmental scientists, including myself, end up being quite detailed in their expertise in one area as well. And so I'm an environmental scientist, and I'm also what would be called a biogeochemist, and that would be my other real disciplinary link. But a biogeochemist tends to be lumped in as an environmental scientist oftentimes anyways. So there you go. I hit two birds with one stone. But lots of environmental scientists gravitate not just from multiple science disciplines. They also pull in things from political science, economics, all sorts of other social science spheres, and pull things into a real environmental science kind of perspective. Because in the end, environmental scientists tend to ask two questions broadly. One is, how do things in the environment affect us? And or how do things that we do to the environment affect everybody else? And animals potentially included and all that. All right, so according to my own grandmother, who just turned 80, I'm an environmentalist, only because she doesn't know the word environmental scientist. And she really doesn't know what that is, but environmentalist makes more sense to her. However, I'm not really, I'm a kind of environmentalist, but I'm not really an environmentalist. I'm actually an environmental scientist. And there's really a pretty clear distinction between those two things. I talk a little bit about this in the book. The most important thing is that most environmentalists are activist kind of types that are hugely biased in their views of how things go about. Not saying that's bad. It's actually useful because there's another entirely biased wing of society for which you kind of need to balance things out. So fine. Environmental scientists and scientists of all disciplines by nature are kind of held to be, at least initially, unbiased in what they're doing. And so I cannot really enter into any kind of study or any kind of experiment hoping and or thinking that something in particular is definitely going to occur. You run into a lot of issues trying to carry things out if you go that way. And so from a scientific perspective, scientists need to be objective. They need to be open to having things happen that they don't necessarily hypothesize about. And so oftentimes hypotheses don't work out, and that's fine. That's how things get advanced half the time, was when mistakes get made and or hypotheses, things that you expected to happen didn't actually happen. That's usually much more interesting than if you plan to walk across the street and you get across the street. All right, not very interesting. If you plan to get across the street and you meet two guys and you get robbed on the way and all these things happen, that's much more interesting. Okay, so things don't necessarily work out as you're expecting, then it's a little bit different. But that's the main distinction between environmentalists and environmental scientists, not necessarily meaning that environmental scientists can't be environmentalists, but this that they're not necessarily so. So I have extremely strong views on the environment that I don't mind giving you, that I feel are scientifically backed up normally, however. But some people go off the rails. Like, I mean, how many of you guys ever watch, I like him, but sometimes I think he goes off the rails. You guys know who David Suzuki is? You ever actually seen him talk? He's crazy. Okay? And I've seen him talk live a few times. He has some really good ideas, and then he goes off the rails every once in a while. He is a scientist, though. He's actually a geneticist. But every once in a while, some of the stuff he does definitely embarks more on the side of environmentalism than it does an environmental scientist. Nothing wrong with it. I'm just throwing it out there for what it is. All right. So at the end of the last class as well, I made you guys all try and get bonus marks, which did not exist, to make a point about how unregulated resource use tends to occur in the environment and what kind of consequences this can have. And what happened essentially is a demonstration of a term called the tragedy of the commons, which is a concept proposed by an ecologist from the University of California, Santa Barbara. Excuse me, that's what UCSB is. Back in the late 60s, a guy named Garrett Hardin. And what it is simply a theory that unregulated exploitation of any resource leads to its depletion. And generally, it's relatively rapid, in a relative sense, depletion. Because what happens is resource users are tempted to increase their use of that resource and or their extraction of that resource as much as they can in relation to the technology they have to do so, oftentimes in drastic opposition to what they see happening in front of their face. So regardless of the fact that sometimes people will see all of the resources are being taken away, they won't care that their buddies up in the halfway up the lecture hall can't get beads. They want to get as many beads as they can for themselves. But the question comes up, is this still really a basis for ongoing environmental issues? I mean, as an example, can we do anything about it? I mean, as an example, your run-of-the-mill company at all, almost any publicly traded company in the world, what is their number one mission? To make as much money as possible at all costs. That is their number one mission. Their number one mission is not to make as much money as possible in relation to how much damage they might do to whatever resource. I mean, I'm talking about resource companies and everything. All right? And so it has nothing necessarily to do on the top side with what's going on. How about something that's going on in the oil sands? Would you think of that as something related to the tragedy of the commons necessarily? Do you think that there's unregulated resource depletion going on out there? Do you think that there's massive quotas on how much oil somebody can produce from the oil sands? Not really. You're given a certain, for the most part, the speed with which oil is being taken out of the ground pretty much anywhere in the world is almost entirely a function of technology. And is almost entirely a function of how quickly and what technology exists to get that stuff out of the ground and refine it as quickly as they can. Not necessarily because there's a lot of government regulations. And frankly, I mean, the Harper government's taken away a lot of regulations the last few years anyways, so it's gotten even a little bit easier. Where government comes in to kind of deal with it is to put some sort of regulation on that exploitation. And so, the theory at least goes that without some sort of intervention from an outside body, like the government, for example, or say a co-op of fishermen coming together to make their own quota system because they have some sort of understanding about what's going on in their own ecosystem that they're pulling from. Without those kind of things, these things will go on to depletion regardless of people pulling the resource out, seeing that it's almost gone. Okay? So a good example of this, and I think it says page 11 in your notes. I was looking over this stuff this morning. It's actually page 12. Sorry about that. I'm sure you can find it. So page 12 in your notes, this thing Rapa Nui. You guys have seen these statues before, TV somewhere, for example. These are the Easter Island statues. So Rapa Nui is the actual name of the island. Everybody, Western society calls it Easter Island. What we have, so the story of Easter Island, for example, goes that there's some European kind of exploration in the 18th century that ended up on Rapa Nui. And when they got there, what they found were these massive statues. That's a big mystery as to how they could possibly get there, because other than these statues, what they found were people essentially living in squalor in caves and absolutely no vegetation or trees on the island from which resources could have been used to get these things there in the first place. So essentially early theories were that they were dropped on the Earth by aliens or something. Because how could this possibly occur? And the real reason it occurred is because the landscape wasn't necessarily like that forever. They had a really, if you look scientifically at things, for example, have you guys ever heard of the term paleoecology? So paleo means old, really. And so there's some studies that have gone on there that have looked at some of the lake sediments on the island. So in lakes, you have a lake, and you have, dust and dirt and pollen, for example, that falls on the lake every year, and it settles down through the water column over time and then falls to the bottom. And then the next year some more falls on it and some more falls on it. And if it's slightly deep lake and the waves don't mess up too much of the sediment in the bottom, you actually get this record over time. And we're talking over hundreds or thousands of years sometimes in lake sediments that you can look in those lake sediments, pull them out, and actually see what's in there. And one of the bigger things for thinking about from an environmental perspective, there's all sorts of isotopes and chemistry things and things you can do. But one of the bigger things that was done here was pollen analysis. So you could actually go through that record and see what was probably there before, because there's no time machine to confirm some of these things, but it's pretty robust technique. You go through and you see recently, grasses, ferns, all sorts of really small vegetation, pollen from those type of things. You see lots of sediment because there's not a lot of, you see lots of sediment accumulation every year because there's not a lot of vegetation holding things back. So there's all sorts of erosion issues and lots of water on the island that moves around, not a lot of vegetation to suck it up. But if you move back in that record, you actually start to see things like giant palm trees from 300 or 400 years ago, and all sorts of other vegetation that used to be on the island. And so what really happened in the end was that there was a really thriving civilization of probably tens of thousands of people when it was kind of rediscovered by some European explorers in the 18th century. There was a couple of thousand people on the island. But back when, there's probably tens of thousands, these massive trees. With trees, you can make canoes, you can make sliders to roll these great big huge statues all around the island if you had enough labor to do so, and rope from the bark to make things to actually pull these things along. And so back when they had them, but without the proper kind of regulation of the exploitation of these resources, specifically these giant palm trees that they used to have on the island, they used them like crazy. And they went and they didn't realize that it took 300 or 400 years to regrow one of these giant palm trees. And regardless of them being right on this relatively small island and seeing that all of these palm trees were vanishing before their eyes, they continued to just use them like crazy. And the next thing you know, they were gone. And then they had no wood left to make canoes, nothing to build with anymore. All of these things. And there was a massive, therefore, downfall in the civilization. They weren't eating the same things because they couldn't get out to sea. They weren't building the same types of places that they had before. And the whole ecology of the island changed and ended up being found as it was. So one example of really the downfall of an entire civilization related to this theory. All right, so my opinion about environmental degradation. Most of the environmental issues that we face today are due to two things. Population growth, well, three things really. Population growth, massive amounts of consumption related to that large population, most of that consumption being in the form of energy, and a lot of that being in the form of non-renewable energy, way above what we can do, so it's not really a renewable stand. And the third point is that we are too stupid to realize it for the most part. And that is a bit of a controversial way to say it. We're too really dumb to see what's going on. I think everybody kind of I think we all probably realize what's going on. You know, I think we all realize that there's a lot of resource extraction going on, that climate change is actually happening in these things. But at the same time, regardless, everyone also seems to be, not everyone, a lot of people seem to be relatively paralyzed to do much about it, which is pretty much the same thing as being relatively ignorant of the fact that it's occurring in the first place. So we can change that, but it involves kind of understanding how things work, and then taking the knowledge of how things work and trying to apply it towards answering these problems. So give you a bit of an idea about the complexity of the issue at hand. This is the idea, one idea about how to numerate or how to put a quantity on how much we are overusing resources, is this idea of the ecological footprint. And what the ecological footprint, how many of you guys have heard of an ecological footprint before? Oh wow, good. This came out when I was in grad school, actually. It's not that old. And I think they start to talk a bit more about it in high school and stuff, so that's good to see. But an ecological footprint, if you don't entirely remember, is taking all of a person's needs on average, say in Toronto or in Canada, taking all of those person's needs for how much they eat, how far they drive their car every day, you know, how they heat their house, all of these different things that actually use resources. Taking all that and then assigning a land area that it would actually take on Earth to garner all those resources that lifestyle is leading. Now, it's actually a very complicated means by which one goes about and gets that. But for the most part, you can think of it in a relatively straightforward context. You know, if you drive long distances every day, it takes more land from which you would need to extract oil to make the gas, and then more land to provide electricity, to refine the oil to make gas, and then to heat your house, and then raise chickens and fish and vegetables and whatever else, and then things to actually feed the animals that you're going to eat for meat, and all these types of things. These things all conglomerate into a relatively large land area for some countries, including ourselves. For example, Canada is right up there. 7.6 hectares per person was the latest, greatest in your book, anyways, estimation of the Canadian average ecological footprint. So what that means is, how big is a hectare? You guys know? You've probably heard acres before, right? Probably don't know how big an acre is though either. Acre's not really that straightforward either. A hectare is actually more of a straightforward, it's the metric, one of the metric areas. So a hectare is 100 meters by 100 meters, which is 10,000 square meters. So the average Canadian needs 76,000 square meters of land to lead the lifestyle that they are currently leading. And you can see, you know, some of the less developed countries, say Rwanda, for example, at 0.7 hectares per person, is largely these things come down to lifestyle, money, and access to resources. And so you can see some of the developing nations with less money, less access to resources, different lifestyles, they tend to have smaller ecological footprints, while, you know, places like Canada and France and the United States have these quite massive ecological footprints. But the scary part of all this is that if you took the ecological footprint of every person in the world and then added them together, you can see on the right-hand side that quite a long time ago, before most of you were born, we passed the point where the ecological footprint of the people living on Earth was actually smaller than the land area on the Earth. So we are at a point right now where the amount of resources we need to continue the lifestyle that we currently live as a globe, as a world, in its entirety is beyond the area that we actually have on Earth. So two options are, one's to inhabit the moon and hope that there's some resources on there, on Mars or something like that. Star Trek, get some sort of ship or something with fusion technology and go off into the universe. I don't think that's going to happen anywhere in the very near future. The other one is to change lifestyles, because how can you possibly have using more resources than there is land area to get those resources from? The main reason is that we are using resources that really aren't meant for us at this time. And so we are kind of betting, our grandchildren's and our children's future by using stuff that's not going to be there. So we are depleting the amount of area that will be useful to future generations by garnering more of it now, which is, a classic kind of baby boomer move. And so try not to continue along these trends. There's some things we're going to talk about through the ages. It's totally possible to use more than is there, but it's not sustainable. All right? The only way to stay sustainable over time is to have an overall ecological footprint that is less than the size of the Earth. That's it. So it's just evidence, essentially, that we are on a massively unsustainable and then continuingly and increasingly unsustainable path. All right, so who cares? Right? So we have this issue, there's environmental degradation. We can't possibly continue on this trend of using resources that we're currently on. Who cares? Well, there's two general, there's lots of opinions on what might happen in the future. There's two polar opposites that you tend to hear for the most part. And then there's middle ground that doesn't really have a name for it. The first is this cornucopian view of the future. And it has a lot to do with how we deal with resources in the present when you have some of these views. One is, the cornucopian view is that it's fine. Everything's going to be fine. We're going to come up with new technologies, for example, to better use the resources we have in the future. So even though we're on a trend right now where we're using more than we actually have, everything's going to be fine because, when the next Bill Gates comes up that's has to do with agriculture or something like that, we're going to be fine. We're going to figure out how to feed the world in perpetuity. Somebody's going to come up with fusion energy and all these types of things, and we're going to be fine. That's a cornucopian view. So meaning that regardless of the challenges we have ahead, we'll figure it out, and everything's going to go on. All right? Think about, not necessarily always the case. Certainly it wasn't the case in Easter Island. They certainly weren't able to come up with an idea about how to grow more trees and figure things out. The other one is this Cassandran view. They talk a little bit about both these things in your textbook, by the way. Cassandra was this mythical princess of Troy who prophesies about all these dire kind of future scenarios, the kind of Nostradamus type stuff. And so a Cassandran viewpoint is simply, throw your arms up in the air and say, we're screwed. And that's essentially what it is. Yeah, please help us, whoever's up in the sky or whatever. And so in that viewpoint, essentially very little is also done sometimes, though, because it's just just a depressive kind of way to think about things. All right, so let's move on a little bit to population. So what we've kind of gone through so far is kind of think about what environmental science is, science in general, think about the basis for a lot of environmental degradation. What I'm going to talk about today is the scope of human population growth, its history. We're going to talk about demography, which is kind of a social science interdiscipline. We're going to talk about a concept called the demographic transition that's important for you guys to understand. We're going to talk about different factors that affect population growth, the effect of population, affluence, and technology on the environment, and the current effects of disease in controlling population growth. So here is one of the the second equation of the year. It's called the IPATS model. All right, something come up with this in the 70s by these guys, Ehrlich and Holdren. And what it is more of a conceptual model. It's kind of like a semi-quantitative equation that can be used to think about how things impact the environment. But from your guys' perspective, I want you to think of it more as a conceptual thing that brings together all of the things that could possibly affect the impact on the environment. And IPATS is kind of easy to remember. So the big things affecting the environment are population, which is P, affluence, which is A, and affluence is how much money you have. Technology is T, and sensitivity of the environment is S. It used to be the IPAT model, then they added an S like 10 years later, and they got another paper out of it somehow. So sometimes you come up with another letter, you can get more publications. So you get this IPATS model. Population. Is there scenarios wherein increasing population can be good for the environment? Not really. And so increasing population is going to be a positive type of number, you can think of it, almost in all senses. So increasing population. If you decrease population, you could have a decreasing impact on overall in the environment. How about affluence? Do people with more money have a larger or lesser impact on the environment? Larger? Lesser? Good. Okay, so more money, generally greater impact on the environment. Not to say that there's no impact on the environment from people who don't have money either, just that it's definitely not nearly as extensive for the most part as people with money. Technology. What about technology? Where does technology come into this? Well, technology can come into this in two different ways, and they're entirely opposite. All right, one can decrease the impact. The other one could actually increase the impact. Okay, so in one sense, excuse me, I have some fall allergies. In one sense, technology could increase impact by producing machines that are better at extracting oil, for example. Then you would have an increasing impact on the environment, or machines that were, able to produce more crappy GMO crops or something like that on larger land areas. Things like this. These are technological impacts that would have a larger impact overall on the environment. What about technology that would actually lessen impacts on the environment? We're talking about things like clean water technologies and technologies that would allow for quicker replacement of renewable resources. Things like this could actually decrease the overall impact on the environment. And if you think of this in a mathematical sense, so this IPATS is a model, and you're multiplying all of these pieces by pieces, if you have something that is having an impact overall on the environment, that number is always going to be greater than 1 that you stick in for one of these terms in the IPATS model. If it is something like technology that could actually decrease the impact on the environment, what is that number going to be? Not negative. Okay? So you're not going to, if you put one negative number in a thing like this, all of a sudden, happy-go-lucky, you have negative impact on the environment, less than zero impact on the environment, and everyone goes home happy. So that's not negative. A fraction, something less than 1. So if you have something that's something in between 0 and 1 in particular. All right, so from a mathematical standpoint, if you had, population, you gave it a number of 10, and affluence, you gave it a number of 5, and sensitivity, you gave number 2. All right, and then you had some sort of technology that could lessen that impact, then your technology might have a number like 0.5, which would pull all those final product of your model, the actual overall numerical impact, down. Just as an example. All right, so how long have human beings, as we understand them, like walking on 2 feet, talking, having a good handle on fire, all of these things, not necessarily what we're talking about up here. How long have humans been around for? Anybody know? How long has the world been around for, from a scientific standpoint? I'm sorry if you have other viewpoints. But from a scientific standpoint, how long has the world been around for? About 4.5 billion years. Good. How long have humans been around for, as we know them now? What do you think? 150 million. No. Yeah, somewhere in the 20, 30,000 area, actually. That we really, maybe up to a little bit more than that, as we kind of really understand intelligent human beings as we know them now. Homo sapiens sapiens. Okay? And so not a long period of time necessarily to have caused a crap load of damage. And most of that damage has actually happened in the last 300 years. And so long, long history, and a lot of stuff has kind of hit the rails in a relatively short period of time from a geological standpoint. But human-type beings have been around for a few million years. And there's a little bit of controversy in exactly what that is. So we're talking about the first kind of human-type beings to evolutionarily break off from your run-of-the-mill chimpanzee, for example. These people have been dated back to in between 4 and 7-ish million years ago. You guys, I'm not going to play it, but you guys heard of Lucy? You guys Beatles? Who's a Beatles fan? Not too many Beatles fans anymore. Lucy in the Sky with Diamonds. You guys know that song? It's actually about the first human being. Actually, no, it's not about the first human being. It was made before the first human being, this Lucy, was discovered. The archaeologists that discovered them were listening to the Beatles song, Lucy in the Sky with Diamonds, and they named her Lucy. No joke. All right, since these first kind of human beings hit the earth, and they learned to have sex with one another and produce more offspring, they have produced more and more people. And the amount of time that it takes to necessarily increase the population, specifically to double the population, can be relatively accurately modeled / calculated. And this is another equation, so a second equation we have here. So the doubling time is equal to ln 2 times 100 over the growth rate in percent. I'm going to give you guys a little bit of a moment right now, okay? Hold on. Who loves equations? Put up your hand. Okay, who hates equations? Put up your hand. Okay, good. As long as you understand what the equation means, I could care less if you remember and memorize an equation. I'm just going to throw that out there right now. Memorization, for the most part, in the real world, 100% useless. Okay? Do I remember everything that I was supposed to memorize in university? Not most of it. Do I still remember all the details about the first 20 elements in the periodic table? Actually, yes, I do. Okay? But it depends on what's kind of important. And there's certain equations that you might find important later on, but that you might, some people have a mental block to remember equations. And I'm in there for some equations for sure. Now, the non-scary part. All your midterms, all your final exams, everybody can bring in one sheet of paper with any equation on it from this class. All right? I'll give you details about it when we get towards midterms. So relax about your being totally scared about seeing all these equations on the board. The more important thing is that you understand how these equations work. Okay? So, ln 2 times 100 over the growth rate. Well, the nice thing is that if you take ln 2, which is a constant, and you times it by 100, which is a constant, you always get the number 70. So really what the equation is 70 divided by the growth rate in a percentage. And so, for example, if you had a growth rate of 1% per year, Okay? Growth rate of 1% per year. How long would it take to double the population? 70 years. Good. Easy as it comes, right? And if you had a growth rate of 2% per year, how long would it take to double the population? 35 years. Easy breezy, right? 70 divided by 2. Not such a scary equation anymore. I saw a couple eyes go like that when we first started, okay? And then if you get out your calculator and you did the current global growth rate, which is 1.2%, what would you get? Pardon? Yeah, something like 58 years, right? Is that what you got? 58-ish years. And so 58 years in our current situation, by the time you guys are 10 years into your retirement, the population could be 14 billion people on Earth at the current rate. And so we're right around 7 billion right now. Actually, I think we're now over 7 billion, regardless of what's on here. So we would double that population. If we keep at our current growth rate, we will double that population in 58 years. Kind of scary. We're having problems already with the number of people on Earth, trying to feed them, trying to make sure there's economic equality across more boards than there currently exists. And if we continue to increase that, that's a bit of an issue. Canada's current growth rate, for example, is 0.9%. So we're talking about 78-ish years to double Canada's population. Canada's population, if you took away all of the balance between immigration and emigration from the country, is negative. And so without immigration, for example, we would have a plummeting population, which, frankly, in Canada, overpopulation is not an issue. Okay? We have 30-ish million, 30-something million people, an enormous country. You know, from a Canada perspective, we may have these large footprints, but we have a large area. But you're going to have to live up in Baffin Island, exactly, right? And so it really is a little bit dependent on how you look at it. But for the most part, immigration is an entirely different deal that's important for the overall economy of the country anyways. And so, but give you an example, the main point I want to make, though, is there are places on Earth where the population is actually declining. Pardon? Yay. Yeah. There are areas where the population is declining. There are areas where the population is actually exploding still. I'll give you an example. China's population growth rate has come down a lot. India's population growth rate is quite high, yes. China's population growth rate used to be like in the high single digits % per year. They come in with a bunch of policies that we'll talk about some other time, including the one-child policy. Now it's down to about 2.8% per year. But their population is already over 1 billion. So we're talking about China potentially being 2 billion people in 25 years, 30 years. So it's not, these timelines are not that long. There's something that you guys, I think, can grasp relatively easily. What makes this equation fall apart? What's the main assumption that you guys can gather from this equation that if is not held true, makes your estimations of doubling time fall apart? Yeah. Right. I think I heard correctly that the growth rate has to be sustained where it is, right? And so if the growth rate changes, your doubling time changes and your calculation changes. So the assumption in this calculation is that the growth rate is stable over relatively long periods of time, including at least the length of time that you're calculating that specific doubling rate. Yeah? Right. Sorry. No, talking about units, that's a good question. Actually, it's kind of the wrong units up here for growth rate. So growth rate says percent. So there's two ways to to express percent. It's good to clear up. Two ways to express a growth rate. One is a fraction per year, and one is a percentage per year. If you use the fraction per year, your doubling rate is going to be huge. Your doubling time is going to be multiplied by 100. So rather than having a doubling rate of 35 years, it's going to be 3,500 years. Okay, so don't use the fraction. So the reason I put percentage up here, which is incorrect to actually put, I should have put percentage per year. Okay, and so it's actually percentage per year is the unit. And so if you take that, you take the inverse, you divide through by something that has year on the bottom, what's your unit? Year. Okay? So that's how you get years out of the whole thing. Is percentage sign a unit? No. Okay, that's the other trick. You guys can learn that in the second tutorial. All right, where we're going to talk about units and stuff. But that's good, really good point to clear up. That's where year actually comes from. So with all these doubling rates, what we've had over history is a relatively stable and small population on Earth up until around the time of the Industrial Revolution. And so if you look at, this is kind of world population up until, say, 2005 kind of area. And you can see that we did not hit 1 billion people until the early 1800s. So approximately 200 years ago is when the world population first crossed the 1 billion mark. And so from, say, 20 or 30,000 years ago until 200 years ago, everything was under 1 billion. And then in the last 200 years, we've gone from 1 billion to over 7 billion. And so what you get with this doubling rate is we call exponential growth. So you get the ski hill type looking graph. And with the ski hill type looking graph, what happens is that when you're doubling larger populations, that speeds up everything. So as your populations get bigger and you double them, it gets bigger, and then you double again. So you it's like 1 times 2 is 2, and 2 times 2 is 4, and 4 times 4 is 16, and 16 times 16 is, what's that, 132? And 132 times 132, that's what we're talking about for growth rate. So that's why the tail end of this chart has gone through the roof. All right, let's have a little break. Come back in 7 minutes. That clock up there says 10:12. We'll come back and we'll keep talking about some of this stuff. So we're talking about population and population increase. Theoretically, there is a limit to how far a population can increase. And some of you have probably learned this in biology before. This limit to how far a population can increase is called its carrying capacity. And so when you have a new population somewhere, or around on Earth, maybe an old population that's continuing to increase and hasn't necessarily reached its carrying capacity, depending on the circumstances, you will get to some maximum number, theoretically, that kind of levels off over time, which is the maximum number of people that some sort of ecosystem can actually sustain over time. There are a number, at this point then, when you get to this standard, your births kind of equal your deaths, and population stays relatively stable. But there's lots of limiting factors at this top end. One is these things include things like water, space, food, predators, and one of the big ones that we find oftentimes in Earth's history is disease. And so things start getting too cramped up, people have to live too close together, you get the bubonic plague come through and wipe out half the population, for example. Not much you can do when you're shoulder to shoulder with people in the underground of Scotland or something like that in Edinburgh, and everyone, you get it and you're done. And that's how things actually get controlled. And so, is it possible that with increasing population on Earth, we could run into such issues? Big time. Okay? These are the kind of things that we are going to face. Things like starvation, necessarily, unless we learn how to produce more food. We have more disease because we will all have to live closer together, and there'll be much more issues with contagions and stuff like that. There'll be much more fights over water and trying to get access to clean drinking water. And all of these things, depending on your situation and your survival of the fittest, will limit overall the population that you get there. Estimations of the world's population at present vary widely, big time widely. And people have placed it at an exorbitantly low and almost hilarious number of 10 million, which is a little bit less than 7 billion. So 10 million people on Earth could essentially live like Bill Gates and Donald Trump. Okay? And that would be the carrying capacity of Earth if kind of like the 1% took over. All right? Or the 0.1% really took over. We would be somewhere on the 10 million area. We're not like that. On the very far end, which is a little bit more realistic but a little bit scary, is that the carrying capacity of Earth could be somewhere in and around 33 billion. So imagine 4.5 times more people than we have right now everywhere on Earth. That would lead to a lot of changes in how your everyday life was carried out, and your job prospects would be even worse, and all sorts of issues. Okay? And so, but we would be able to carry that. We would not be able to carry that population at the same lifestyle that is currently being led by people on Earth. This carrying capacity would essentially be survival, not survival in comfort. All right? And so there's vastly different scenarios there. The issue with carrying capacity in an unfortunate sense is that it's very uncertain as to whether or not that leveling off is going to occur, or if there's going to be some sort of feedback in that system that is going to cause something a little bit more surprising and necessarily a little bit more deadly, for example. You can see, so a lot of these models of carrying capacity are carried out on certain simple organisms like yeast in your upper left-hand corner. And so in the upper left-hand corner, you see this exponential growth, and then things get kind of smushy in there, and then population levels off, and you get your normal carrying capacity curve. But there's a lot of kind of feast or famine cycles that have been shown to occur in nature rather than having this kind of steady line. And these all have to do with feedbacks. And so you have a positive feedback where the population gets really hammered for a while, and then something negative kicks it back up. And that's necessarily what that is. Positive, kind of a negative feedback system is what you get at this sustained level of population, kind of back and forth, back and forth, back and forth, kind of homeostatic relationship where you're not necessarily a straight line, but you're kind of relatively tight around that straight line. However, there's lots of scenarios that we've seen in nature wherein either there's a bomb, and not a bomb, but I mean literally the population bombs and goes down drastically, very quickly, like the right-hand scenario about the St. Paul reindeer. Increasing population, something bad happens, boom, population goes down to close to zero in a relatively short period of time. That's a little bit abnormal. We wouldn't want to see that for ourselves. Who knows, though? A little bit more normal than both of those case scenarios are the ones on the bottom left and the upper right, which show some sort of steady state, maybe. It's a little bit of a trend in that steady state, either going down or going up after you've reached some population maximum. But the problem is that rather than being kind of tight around that line, it's extremely erratic around that line. So whereas you have these kind of flip-flop positive, negative feedback scenarios, where it's not, negative feedbacks are great. Things kind of stay stable and you're good. For the environment, for people, trust me, you love negative feedbacks. The word negative sounds negative, but you love negative feedbacks. Things stay stable and everything's cool. Positive feedbacks in nature are brutal. Okay? Positive feedbacks in nature cause things to move quickly in one direction, oftentimes in a very exponential sense. And so what happens is you will get these populations come up and then crash, and then come up again and crash. And oftentimes what happens is there is necessarily, and this is something that I could possibly see happening with the human race. What happens is, race, all this stuff, technology, iPads, food, whatever, and you get up to this population and then some big disease hits. And there is really an upper limit. Disease hits, boom, you're down 3 billion people. But then you recover, and you get this really cool president that comes on or something and rallies everybody, and you print a bunch of money, and then the population goes up, and then boom, you get to that point again, big disease comes in, pop, you're down. This is something that happens a little bit more with these other two scenarios, and potentially, it really depends. It's scary, but potentially what could occur in the very, very long term with us. But, and there's always a but. I want to say but almost between every slide here. We have seen what are called increases in carrying capacity. These episodes of increases in carrying capacity through history on at least 4 occasions that we can easily document, wherein rather than reaching some sort of carrying capacity or potentially having some sort of massive drop in numbers, we've come up with new technologies usually that have allowed us to increase that carrying capacity. So rather than getting to a point where we're stable, we get to a point where we're kind of stable, and then we figure out how to make, not iPads, they don't really increase our population, but some sort of new technology like, influenza vaccines and things like that, where you can kind of come up and then you pop up, and then you're up here, and then you figure something else out and you pop up. And that's a little bit more about how human population, at least in the longer term over history of humans, it's a little bit less certain now because population is increasing so quickly that it would require us to be churning out new technologies to fight these kind of carrying capacities kind of every second of our lives. And so it's becoming a little bit more difficult. And so what you get are these kind of technological changes and these leaps in carrying capacity. And so I'll talk about each of these a little bit. The first one was in the Paleolithic period called the Cultural Revolution. So you can think about essentially kind of Neanderthalic man running around grunting at each other, pulling the ladies around by their hair, Flintstone style, all this kind of stuff back in the day. And then, and getting to really just some sort of population, sustained population where they're not smart enough to keep themselves from being sick. And so births start to equal deaths. They get to this carrying capacity back in you're talking thousands of years ago necessarily. And we get this carrying capacity. And then some smart caveman thinks, well, I'm going to make a tool out of some bone or some wood. I'm going to learn how to light a fire. All of these very early kind of technological changes. So mostly fire and making tools led to a relatively large increase in population because it allowed for a more varied diet, so it led to less starvation risk. There's some development of speech and communication because there was some very rudimentary trading that had to come in. And some of the tool makings even goes back as far as 2+ million years ago. But we don't have a very good handle on how much this increased population, a little bit theoretical as to what that actual number could be. The next one, which is a little bit more contemporary, is the agricultural revolution. And so up to this point, before this point, you're talking about largely nomadic lifestyles, hunters going around and killing things, living in caves, maybe some sort of rudimentary dwellings, building fires, having some tools, stuff like that. And then some Bill Gates of his time came around and said, look, and I can put some seeds in my backyard and they grow corn or they grow whatever, and you start getting the first farmers. And so the real manipulation both of animals from a livestock perspective and the manipulation of food from a cropping, farming type of perspective allowed for another kind of increase in that carrying capacity because you could feed more people. So theoretically, before the agricultural revolution, you had a carrying capacity that was probably largely limited by food. And a lot of the carrying capacity, food is a really big deal. And so what you got after the agricultural revolution was a little bit of a reduction in the area needed per person. So you didn't have these vast plains on which you needed to hunt. You necessarily had a little farm that you grew food in, and you had some animal husbandry and things like this. Population density therefore increased hugely, like up to say 500 times. For the first time in history, there was more food available than could actually be eaten, which was a big deal. And also started to get the establishment of areas of society that didn't necessarily just rely on growing food. You started to have professional people, like more priests and lawyers and all these type of things, shopkeepers and stuff. And so society would actually kind of increase. And because it was easier to meet all these demands, you get a population increase, you get that carrying capacity kind of goes over. But sometimes, I got this Fertile Crescent thing on here. We'll talk about that later. Sometimes people aren't so smart, so they try, and the Fertile Crescent's kind of Middle East kind of area, pretty dry. A lot of irrigation farming back a long time ago that worked out really well for the society at the time. Think like American Midwest right now. But what happens over time? What's in water from that when you spray it on the ground? Even fresh water. Minute amounts of salt, even in fresh water, when you put it on the ground, right? So if you get a bottle of Evian water or something that you drink, and it says, minerals inside there, sodium, all that kind of stuff. If you took that bottle and dried it out in the oven or evaporating it or something like that, at the bottom would be a little bit of a white dust, which is literally salt. And so if you continue to irrigate, for example, some place that's super dry, and so you add water, most of it goes up in the air through evaporation, salt's left behind. Add water, salt. Water, salt. You do this for decades or potentially hundreds of years, what you get is salt water or a very salty soil on the environment. And so sometimes you can try, but you're limited by necessarily some sort of technological know-how and or understanding of what the potential consequences could be until later. And then you get a very serious collapse in the society that might have actually been depending on that food resource. So not always great. Whoop. The next big population increase was during the Industrial Revolution, which really began in the mid-18th century in Great Britain. And this worked out from a little bit of a transition from two things. One, a little bit of a transition from the rural community into the urban community, but you had more technology as well. And so, what you ended up with were not always necessarily some better ways to make in faster ways to make food, but also better ways to combat disease, for example. So better sanitation. You started having, actually having toilets and things like this. Better medicines. And even some advances in agriculture related specifically to motorized technology. So you're able to start to move from having a horse do everything in your farm to maybe even the first kind of motorized thing that could could separate your grain or something like that. And then you start seeing the first kind of accumulations of wealth, the kind of first inklings of that 1% starting to take over the world. And now we're in the middle of this one, which is the kind of medical technological revolution. And we've really kind of raised the limits on population growth quite a bit, largely through development of massive amounts of new medicines and pharmaceuticals that allow people to live longer, somewhat healthier lives, hugely improved sanitation over, say, the industrial period, global communication, for example, whatever, a little bit, increase in population a little bit. One of the biggest things is termed the Green Revolution, which is agricultural advances. And this includes, these are hugely important, things like pesticides development, genetically modified foods, all of these types of things that have allowed yields, not necessarily with no consequences, but have allowed yields to increase dramatically from an agricultural standpoint, such that we can actually continue to feed more and more people. Okay, so that's kind of what we've seen technology do. So from a standpoint of what we learned earlier, you almost have, we've had these kind of cornucopian type events happen through history where our limits on what we can do or what we're doing to the environment have been somewhat lifted by new technologies. Whether or not that trend is going to continue, I'm not sure. But the other thing you should notice is that the time in between those new advances in our ability to have larger carrying capacities have gotten shorter and shorter. We're talking about millions of years ago to, say, 10,000 years ago is the first kind of, between those first two. And then 10,000 years ago to about 300 years ago, 250 years ago for that second and third one. And then we're talking about 250 to now. And so those times keep getting much and much shorter in between. And so we're also, like I said earlier, combating an ability to have to come up with these two new technologies at a quicker pace because the population's increasing at a much quicker pace as well. Okay, so let's talk a little bit about demography, which is the study of human populations. And so I'll give you an example of population growth and density. So there's lots of spatial variation in where we see lots of people and in how many people are smushed into a certain area. So you can see, for example, where are the growth rates highest in the world? In mostly Africa and kind of Southwest Asia kind of area. Okay? These are generally what you'll find our growth rates are highest where GDP is lowest. And so growth rates are quite well related to how much money there is around, and which relates to hope for the future / access to contraception, education of women, all sorts of different things that we'll talk about as we go along. And then what do you kind of notice in terms of population density on the bottom? So that's how many people live in a square kilometer. The red being where there's lots, and the white being where there's almost none. So you can see we have lots of places in Canada where there's almost nobody there. You wouldn't want to be there anyways. And then there's some places in Canada, right around Toronto is probably the only red dot, one of the only red dots in the entire country. What else do you notice? There's two things. One, China and India stick out like a big sore thumb in terms of population density, huge populations, relatively large countries in comparison to lots of other countries in the world, but this really, really large populations. You can also see that people tend to congregate a lot around water. And so population density, because water is a massive resource both for food and for transportation, things like that, and for getting things in. And so you can see that there's not necessarily that there's also the biggest population density where the largest growth rates are. All right? Some of the population density is a function of history, and some of the population density is a function of death rates versus birth rates and things like that as well. I'll throw a couple of these at you on tests, for example, and ask you to talk about them a little bit. These are age diagrams. And what these age diagrams are is on the bottom of these diagrams is the number of people that are in each category. And up the left-hand side of these diagrams are different age groups. And they might be in 5 or 10-year increments. And just by looking at these shapes of these age diagrams, you can tell mostly whether or not there's a large potential for that population to increase rapidly, to decrease, to relatively remain stable, and to almost tell who's in charge of what's going on. So if you have a very pyramid-y type age diagram where it's fat on the bottom, so lots of people who are young, you will have rapidly increasing populations. So that's the one on your left. If that pyramid narrows up a little bit, you will have increasing populations which are relatively slowly increasing compared to the situation on the far left. If you squeeze that even more, such that there are almost equal populations as you go up, but it will always, almost always, in this scenario, decrease as you go up simply because older people die more than younger people do. And so you will have an even more squeezed kind of triangle somewhat. You'll have, that's a stable population. And then on the far right-hand side, where you have a larger, fatter area somewhere in the middle, and your two ends tend to be smaller than you have in your middle, you will have decreasing populations. Okay? And so think of these in a relative sense. It would be very difficult for me to show you, say, the second one and say, is that increasing quickly or is it increasing slowly? I'm not going to ask you that, okay? Because that would be a little bit crude. But I would be curious for you to tell me, if I looked at number 2 from the left and the one on the furthest right, and which is increasing more quickly, you would be able to tell me. All right? Why is it important that these things, when there's more young people that are there, why is the population increasing more? Well, you can tell if there's lots more babies, then that population is increasing. Also, if there's lots of people in and around their 20s who tend to have sex that makes babies, then their populations are also going to increase much more quickly as well. All right, so a couple of examples. So, relatively similar size populations overall. Say Madagascar on the right and Canada on the left. And you can see Canada has this kind of fat in the middle structure. So who are those people in the middle? What do we commonly refer to them as? Baby boomers, okay? And maybe even that's even going up a little bit. So that's all the people we get to take care of for the rest of our lives as they suck up all our money and resources, okay? And then in Madagascar, for example, you have this massively fat part on the bottom that shows that there's lots of babies being born, and the population is increasing dramatically. So relatively stable / decreasing population if this did not take into account, because this does not mostly take into account immigration statistics, versus Madagascar on the right, which is massively increasing, but similar overall sizes of populations. All right, quick question. Whom are born more, boys or girls? Who says boys? Who says girls? Okay, so I have 2 girls and 0 boys. But I will tell you right now, boys are born more often than girls are on average in the world. Why are boys born more often than girls? That happens. Let's say without, and we will talk a little bit about this, without the intervention of preventative abortion of girls, are boys more than girls? Yes, they are. Okay, regardless, there's about 106 boys born for every girl born in the world. Why is there more boys born than girls? Yeah. What's that? Faster? No. Because who's clumsier when they're kids? Who does more dangerous sports? Who dies more before they produce more babies? So there are more boys as an evolutionary trend born than girls because we are the dumber sex and the clumsier sex that tends to die off more often than girls before we get to an age where we can reproduce. So on average, by the time you looked at those same babies on reproductive ages, they're necessarily close, they're quite close to 1-to-1 in most areas, but at baby level, there is a slight bias towards boys. So about 106 males to every 100 females born. But yes, there are issues around somewhere like preventative abortion. So in certain cultures, for example, boys are better than girls to their parents. And there's very few cultures I know of anyways where girls are way better than boys. Although I have a twin brother, he has 2 boys, I have 2 girls. I prefer having girls, I can tell you that. It's definitely for kids anyways. But in China, there's about 120 boys born for every 100 girls. What's happening there? Yep. Yeah, it's a confluence of both regulation and culture, wherein the male babies can kind of carry on the family name and tradition, take care of their parents a little bit more, and they have this one-child policy where you're only really supposed to have 1 kid. And so there is some what we call selective abortion that happens. Dirty truth, but it's the truth. Numbers play out. There's no possible evolutionary way that that's not going on. Is China the worst place in the world? Not even friggin' close. Okay? United Arab Emirates and Qatar. The ratios are 200 to 1. 2 to 1. Sorry, 200 babies to 100 babies are born male in a couple different places in the Middle East. And these are, without a doubt, by selective abortion and by, and it's a cultural thing. But it is what it is in one sense. But in one sense, this causes massive population issues. What is the biggest population issue by having twice as many boys as girls? Yeah. Hopefully at least 50% of those guys don't find wives in the end. Okay? Which makes an issue going forward in the end. So there's surprising things that happen as time goes on and as technologies change more or less as well. What we find in not in any culture, but in most countries and in most cultures, over time, we've seen this phenomenon called the demographic transition. And it depends on where a culture or a country actually lies on that demographic transition as to what things happen. And so when, early on in the demographic transition, is when kind of, nation might be kind of poor, technology might not be kind of integrated very much whatsoever, birth rates would be very high, so fertility is very high, and what you get are lots and lots of births, but on the flip side you get lots and lots of deaths, all right, from lack of medicine, lack of sanitation, all sorts of things. And so in the pre-kind of industrial stage, this early kind of left part of this graph area, what you find are high birth rates, high death rates that lead to a relatively stable population and a relatively high and stable growth rate. This is terrible. Not a relatively high and stable growth rate. It says growth rate there. That should actually be slightly different. It's not really a growth rate. Don't even worry, but it's on the left-hand axis here. We have high birth rates, high death rates, relatively stable population. Okay? I would like to say it's population on the left-hand axis, but it's not even population on the left-hand axis. Okay? So in that area, relatively stable population, high birth rates, high death rates. What usually happens is people figure out how to get access to better medicines, better technology, and better sanitation before they necessarily adjust how many babies they're having. And so you get in this transition period in places, and we've seen it in Canada's history before. It's going on in lots of different countries in the world currently, where you get to kind of this transitional stage where there becomes better access to sanitation, better access to medicine, but birth rates continue to be quite large. And so death rates plummet, but birth rates stay quite high. And because birth rates stay quite high and death rates plummet, the difference between those becomes larger. And you get a relatively large increase in population. And so that is when the population growth rate actually increases. And then people tend to figure, well, we don't need all these babies we're having. We have all these we have a tractor now, and we have all these different types of things that we don't need to have 15 kids anymore to run the farm, and et cetera, et cetera. And so birth rates in this third stage, called the industrial stage, also start to fall off. And so the population growth rate is still relatively high, but it starts to decrease over this period as the death rates and the birth rates start to go towards each other again. And then in the final period, which is called the post-industrial stage, you get to a relatively low growth rate where birth rates and death rates are quite close to one another. And so it's this transition period where you find certain countries, for example, even currently, they're in that transition period now. And that's a lot of these countries where I showed earlier where growth rates are quite high. A lot of those countries are in this transition period where their access maybe to sanitation and medicine is not quite as high, but their birth rates are still high. Or their access to that sanitation then changes and their medicine changes, but their birth rates are staying high and those population growth rates stay high. Whereas we in Canada right now are definitely in this post-industrial stage, but we went through. I mean, my wife has 51 first cousins on one side, meaning that, so she's French-Canadian. She doesn't speak French at all anymore, but I mean her background's French-Canadian, Catholic. They would have, her grandmother had 13 kids, and of those 13 kids, 6 or 7 of them had 10 or 11 kids. And then, so you end up with lots. This lady had 52 grandkids, and you have these huge families. Does that occur as much anymore? Not really. But only a couple generations ago, even Canada was in this transitional stage where that was definitely much more so the case. But is it universal? You know, it's occurred quite universally through Europe, the United States, Canada, say Japan, and a few other nations over the last 100, I would say even 100 to 200 years, more than the last 200 to 300 years. But it depends. That whole system could break down in certain cultures that, for example, place much more cultural emphasis on childbirth or more value on childbirth. And it also depends a lot on, say, the relative amount of freedom given to women in relationships in certain cultures and what kind of choices can be made there. As an example, there's lots and lots of data that shows that education of women and status of women, as well as access to family planning like contraception, can have massive differences in population growth rates, even in places that are quite close to one another. So for example, in Iraq versus Iran, up on that right-hand side, the top left, you can see right next to each other, but with more kind of education. In Iran, for example, the fertility rate has dropped, still quite decently high. Bangladesh and Pakistan, you can see some differences. Dominican Republic and Haiti, they take up one island in the Caribbean. Quite big differences. And what we see overall, generally, is that fertility rate, so meaning how many children are born per woman in the country, the fertility rate drops off quite drastically as education increases of women in particular. Another big factor is poverty. So, like I showed before, most of the places where population growth rates are high are generally where GDP of those countries or gross domestic product is low, so the economy is not very good in most of these countries. About 82% of the world's population lives in what we term developing countries. So quite a large proportion that we can see here. So for example, total fertility rates on the left and gross domestic product per capita is on the bottom. So other than a couple of little deviations there for, say, Saudi Arabia and Israel, for the most part, as the richness in a country goes up, the number of children born per woman in the country goes down. 99% of the next 1 billion people born on Earth will be in developing countries. And only 1% of the next billion people born on Earth that increase the population will be in developed countries. And so it's somewhat perpetuating unless there's some sort of intervention. And so one of the problems is somewhat too is that much of these places where population is increasing quite rapidly are quite sensitive areas in the world as well. So we didn't really, I don't think I actually mentioned the S part that much of the IPATS model. So sensitivity. Sensitivity are places, it comes down to where people are and whether or not that ecosystem is more sensitive to impacts on the environment or not. I'll give you a drastic example. If we had an oil spill in the back of this campus versus an oil spill in the Arctic, which of those two places would be more sensitive to the oil spill? We would see more impact here because there's lots of people, but the Arctic is more sensitive, all right? And is less able to deal with that incoming type of thing. A lot of these places, specifically in sub-Saharan Africa, for example, are really sensitive. So the Sahara Desert itself, sensitive or unsensitive to environmental pollution, you think? Super unsensitive, actually. All right, so the Sahara Desert, not very sensitive. The edges of the Sahara Desert, super duper sensitive. All right, so the edges of the Sahara Desert where it's on the brink of either being fertile or becoming desert, depending on how it's handled, are super, super sensitive areas. And a lot of the population that's increasing quite rapidly in Africa is in sub-Saharan Africa, which is kind of on the edges of the Saharan desert in these areas that are actually very, very sensitive to environmental degradation. And then another big factor affecting growth is disease, especially HIV/AIDS. So one of the things that are making population go down. It's really kind of ridiculous, actually. I'll give you an example. 1 in 5 people in our, I'll put myself in the same demographic as you guys, in Southern Africa have HIV/AIDS, okay, have been diagnosed, 1 in 5. Meaning that 100 people in this lecture hall right now would have HIV/AIDS if we were in Africa, which is pretty nuts. So depending on where you are, there's some things that are coming through, and so mortality is actually rising in certain parts of the areas that are actually going against some of the long-held thoughts about the demographic transition, where mortality would actually decrease over time as any one system develops. And it's also a really big growing problem in Eastern Europe and certain parts of Asia as well. All right, there's a few glimmers of hope, and I'll end it here in a second. So population's going up, growth rates are declining almost everywhere, apart from a few different places here and there where they're still going up quite big. And women's rights and access to education are being expanded in many places, which will have good benefits on population and the impacts that these things have in our environment. I've got a link here. I'm not going to show it because it's kind of like 15 minutes long. We have 3 minutes left in class. But I have a link here to a UN video about the Millennium Goals Project. And the Millennium Goals Project was a big kind of international thing to put through some new standards on, I got one more slide, put some new standards on some specific things. It came through, I can't remember what year, it's almost 10 years. It's one of these kind of bureaucratic, maybe it's going to happen, maybe it's not going to happen kind of things. But the last report card, this is their last report card. And what it comes down to, and a lot of these things are interrelated to impacts on the environment. And what it comes down to are a few things. One of them is eradicating poverty, and then achieving universal primary education, promoting gender equality and empowering women, reducing child mortality, improving mental health, combating disease, ensuring environmental sustainability, and developing a global partnership for development. The things that have been best handled are probably the bureaucratic stuff, like developing a global partnership for development. But ensuring environmental sustainability has been not too bad. And some of the things about reducing poverty have also gone quite well. In this graph, all the green things are improving or at least gathering steam or have met the goals they had set for them around there. The yellow ones are not on current track to meet those goals and or have not yet met those goals. And then the red ones, there's no way in hell they're going to reach the goals. And so these are the really bad ones, including HIV, AIDS, and disease prevention in certain periods. So end it on there. Next week, I think we're going to get into some biogeochemical cycling and how the Earth works.